At some point in the history of math, somebody said, what is the volume of this pair? And then all mathematicians everywhere dedicated themselves to this problem. And a genius came up with this idea. Let's take the pair and let's turn it on its side. Now, let's superimpose an axis on top of the pair. A y-axis and an x-axis. Let's find out the equation of the line represented by this slice of the pear here. We already know from basic calculus how to find the area of this little bit of pear here, but that's an area, not a volume. It's got no depth. Now normally with volume we take the area of the cross section and then we multiply by how far back it's gone, sort of push this square backwards through the depth of the object in order to create a volume. Now we can't do that here because we're not taking our slice of pear and just pushing it backwards like that. That would create a sort of, well, I don't know what that is, a long hill, not a pear. The way to create the pear is actually to rotate this graph, fix the endpoints and let it spin around the x-axis back to here. So each point spins round a bit like a skipping rope coming round, and it ends up here like this. So the graph of the blue function, the blue graph, is going around the x-axis like a skipping rope and ending up here. And if we do that and keep going all the way round, 2 pi rotation equals pear. And that's how we make the pear. So how do we use that idea to find the volume of the pear? Let's have a look at this example where I've used the graph of y equals x squared. So I've rotated the graph 2 pi around the x-axis and created this sort of nice cone-shaped thing. And I want to find the volume. Well, you can imagine it as lots of slices like this, and if I just take that first slice and investigate that individually, we can think about what its volume is and then maybe add up the volumes of all of these individual discs, which overall make the whole volume. So let's think about the volume of this individual piece here. It's a circle, so its area is pi r squared, and then to get the volume of the disc we multiply by the depth. Now the depth I didn't specify, but I'm just going to call it a little bit of x, So the volume of this disc is pi r squared times a little bit of x, so the only thing I need to know is what is the radius. Here's the radius, k. Now actually, for that radius to make a bit more sense and for me to see what that radius is, I'm going to turn it back the other way round. Aha, now that radius is the y-coordinate of the original graph of y equals x squared. Here's the graph of y equals x squared coming up. I was at the point x is 2, so the height here would be 2 squared, which is 4. The height of this disc in here, well, if that's, say, 1.8, down there x is 1.8, then this radius of this disc here would be 1.8 squared, or whatever I just said that x was. If this is 1.5, this radius would be 1.5 squared. If this is 1, this radius would be 1 squared, etc, etc, etc. So the radius of the disc is always the y-coordinate of the function for that particular x. So in general, if we take a disc and try to work out its volume, what we're going to have is that the volume is equal to the area of the top, which is pi radius, which is the y-coordinate, squared, and then times the depth of the disc, which is delta x, a little bit of x. In order to get the volume of the whole shape, we're going to have to add all of these up. So we will take all these little x's, that one, that one, that one, that one, that one, that one, to create all the discs. And then we will, for each disc, work out what pi r squared delta x is, and then add up all of those individual discs to get the volume of the whole thing. And obviously, the more discs we take, just like the trapezium rule in C2, the more discs we take, the more x's we take along the x-axis, then the finer, the thinner the delta x is going to be, and the closer and closer our volume that we're adding up here will be to the true volume, and the true volume, just like how the trapezium rule represents true area, will equal the integral of pi y squared dx. And that's the formula that you can use for working out the volume of your pair. So long as we know the equation of the curve representing the cross section of the shape, we can find the volumes of some pretty nice shapes using this method. So you just rotate round, and this cross-sectional area represented by this curve here creates this beautiful shape here. But all you need to actually know is the formula pi r squared. The pi can come out because it's a number, the r, the radius, is the y coordinate, and we're squaring it pi r squared dx from this point to this point. That gives you a cross-section which you then rotate to get the volume. So it's a really easy formula to remember. Pi r squared. R is y. So if I want to find out the volume of this melon, then I set up my integral. I'm going from 0 at this end all the way over to, I'm not sure what that is, 8.8 I think, 8.8, and I do pi y, which is f of x, which is the square root of 8.8 squared minus x minus 11.1 squared over 1.26 squared. That's the equation of this curve. And that's y, so then I square it and then just go ahead and do my integration and get the volume of the melon.